Right, good evening. We'll go on with the next part of the mechanics course, which is looking at different types of forces. Again, hopefully it'll fit in with the GCSE work you've already done in the physics, and possibly if you're doing physics this year, some of the work you're already doing. So then, it follows the examples in the book. The book starts off by talking about, just introduces driving force and braking force. So specifically, if you're looking at a car, if you're looking at a bicycle, a train, anything which is locomotive, a driving force produced by the engine or the legs of someone pedaling, and the braking force actually applying the brakes of something, as opposed from what might be a frictional force or a resistive force just by the action of something sliding across the surface. Now, clearly, you're probably thinking, well, there are lots more forces we already know, so I thought we might as well introduce them towards the beginning. So, if you have something in contact with a surface, if you have something set on top of a surface like that, we might find there are two forces. There is a upwards force called the normal reaction force, which we're going to come into, I think, in the next chapter. And if something tries to slide across a surface, there'll be a frictional force. Now, those two forces are the contact forces. One's perpendicular to the surface, normal to it. So in this case, normal means not every day. Normal means at right angles. And we get a force parallel to the surface, which is the frictional force, okay? And in next year's work, we're going to link those two forces together. We're going to get a measure for the roughness of a surface. In a string, an elastic band, or a spring being stretched, if you've got something hanging on a string, if you're pulling something with a string, there is a tension in the string, okay? If you're poking something with a stick, or something's sat on top of a column, so that column is pushing it up, that force is called a thrust. Just a caveat here, do not poke things with sticks, okay? That'd be dangerous. The force due to gravity is called weight. Weight is the force, mass is not a force, mass is a scalar quantity. If something travels through a liquid or air, it usually experiences a resistance. We might talk about air resistance, we might talk about drag. And another caveat here, RuPaul's Drag Race, it vastly misleading the title. It turns out to be nothing to do with air resistance, okay? Just be warned if you come across that. So the examples in the book are, I just won't run through them, so you can pause that one and read it. Okay, starting point is a diagram of the forces. So we had a driving force, so the engine produces a force driving it forwards. There is a total resistance to motion, which could be the friction of the bearings in the car, it could be the air resistance, it could be friction. The total resistance is 600. Okay, just by the car traveling up, those two forces. Forces which are irrelevant this time are the car's weight, which would be vertically downwards, and a reaction force with the road upwards. Okay, they're irrelevant this time. What else are we told? There's an acceleration. Accelerations go on diagrams with a double-headed arrow like that. Okay, so the forces acting on the object, with arrows from the object. Acceleration is a double-headed arrow there. Right, how do we answer the question? Newton's second law, with an arrow saying what direction we've got it working in. Newton's second law is the resultant force, another R force there, the resultant force, the sum of the forces, is the mass times the acceleration, which gives us the mass of 950 kilograms, units in that. In the second part of the question, the car starts to brake, so there's a braking force added, a braking force to go with the air resistance, the friction of the road, blah, 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 and there is now a deceleration of 2.5 meters a second squared. And notice how carefully I'm being with the directions that everything is in. Newton's second law applied in the direction of the acceleration. has both of those being positive because they are both in that direction, is equal to the mass, which we've just calculated, multiplied by 2.5, which is positive because it's in that direction, okay? So in this first version of it, I've counted to the left positive. Gives you a braking force of 1775 to the left. If, however, you decided to do Newton's second law to the right, nothing wrong with doing that. You'd have a braking force which is in that direction, negative 600, the resistance. The mass does not have a sign. Mass is positive always, but the acceleration would now be negative, and you would get an identical answer that x, the value of x, is 1775, the size of it. Okay. Second example, a small toy of mass 230 grams. Right, grams, not kilograms. Initial speed of 8. A smooth floor. How long would it take to travel 6 meters? It actually travels the 6 meters in that time. Find the magnitude of the frictional force. Right, read that, underline the important bits. Right, how do I do this one? Okay, if we've used the word smooth, that implies not just a little bit smooth, absolutely smooth. Smooth implies no friction. The fact that we're going to model it as a particle will imply no air resistance. Surface is smooth, no friction. Object is a particle, no air resistance. No resistive forces, no acceleration. So 8 meters a second, traveling 6 meters in 0.75 seconds. So there's some assumptions in the first bit. It actually takes 0.82 seconds to travel the 6 meters. It has an initial speed of 8. Does it say that it comes to rest? No, it does not. We cannot say, like I mistakenly wrote there, we cannot say that it comes to rest. We can say it travels 6 meters. So what did the question want? It wanted the frictional force. Well, here's the first example. Actually, I can't remember what we did last week. Here's an example where we're going to link the suvat to Newton's second law. So what links suvat and Newton's second law? The fact that they both contain acceleration. Okay, Newton's second law, F equals ma. The suvat equation's constant acceleration. So in this case, we've got s, we've got u, we've got t, we want a. S equals ut plus half a t squared. Soak under tap half a square t bag. Put all the numbers in, rearrange, and you get an acceleration of minus 1.67. If we apply Newton's second law to the left, so the acceleration and the frictional force are in the same direction, we can treat them both as positive, and we get a frictional force of 0.383 newtons. Now again on the diagram, these two forces are irrelevant this time, because in year 12 we are not going to link friction and normal reaction, but next year we will. Next example, by all means read the example, pause it, then come back to it. So two people using horizontal ropes to pull a box as shown in the diagram. Can I point out the diagram doesn't say whether we're looking down on something or across at something, so I am not going to add, even though they would be, I'm not going to add a weight and a normal reaction, because there's nothing to tell us that that diagram is actually looking across at something or down at something. So I'm not adding them because they're not relevant, and I don't know where I would add them anyway. What have we got this time? We've got mass, one tension, and an acceleration. So what are we going to do? We've got a mixture of force, we've got acceleration, we've got, we want tensions. Simply Newton's second law in that direction. If it looks unbalanced, it's because there are no resistive forces, so there is nothing to add in that direction. I've added the acceleration with a double-headed arrow, Newton's second law, resultant force, and R force, resultant force, the sum of them, giving that tension. Right, at this point, it'd be worth reminding us that a rope, a cable, a string, a rod if you're pulling something, a spring if you're pulling something, they all have tensions in them. They're usually described as light. Why? It's because we don't have to, their mass will be negligible compared to the thing they're pulling. We can ignore their mass in Newton's second law. That's what the word light means. Light in reference to their mass being negligible. Inextensible, if a string's inextensible, if two things are on both ends of a string, if it doesn't stretch, when that one moves, that one's going to move at the same time, okay? An inextensible, no stretch. Either end of it moves at the same rate. You can only have a tension in a rope, in a cable, in a string, but in something that is rigid, you can either have a tension, a pulling force, or you can have a thrust, a pushing force, okay? Tension and thrust. Right, last example, I think a slightly longer one. Read that. Mass, tension, friction. It's on the horizontal. Find acceleration if, and the time it takes to accelerate to 2.1, if it has a constant speed, what tension is required, and then part C. Let's have a look how we do all that. Right, part A. Find the acceleration if we know the forces. Always start with a diagram. I've marked in the two irrelevant ones just because the more times you see them, the more used to them you'll be when we come to use them. Acceleration as a double-headed arrow. Newton's second law in the direction we're applying it. Resultant force, mass times acceleration, acceleration. Then we can do the second part of the question. What links forces acceleration to the other kinematics things? Newton's second law, and then sue that. List what we know. Label, say what we want to find. Pick the right Suvat equation. They're given to you on the formula sheet. Use it. Right, the second part of the question. If we have constant speed, we'll be careful here. Constant speed and travelling in a straight line implies velocity. I think they've been a little bit slack there. Constant velocity implies no acceleration. No acceleration implies the resultant force is zero. What does that mean? It implies they're in balance. Okay, and I'll use that notation to say I'm balancing left and right. You could equally say Newton's second law applied to the right says that the resultant force is zero. Mass times acceleration, acceleration of zero, and you get the same answer. Part C. Right, let's now read that one. Boy now makes the box slow down and it comes to rest after travelling 0.8. So now would imply from that constant speed of air. So what we're going to do, find the force and say whether it's tension or thrust. Well, notice that we've been given some Suvat quantities and we're asked for a force. So it's going to be Suvat, then Newton's second law. Which Suvat? V squared is u squared plus 2as. Gives that acceleration. Draw a diagram, please. Always draw a diagram. Putting all the directions in clearly. Now, since the acceleration's to the left, I'm going to do Newton's second law to the left. So I've got a positive force, a negative one. 7 take t is 2.76 times 3.2. That's the mass. The other one's the acceleration. Because I'm working to the left, I put the acceleration in as positive. You get an answer that t is minus 1.82. So my assumption that the boy is still pulling with his stick to the right Actually, the video is the wrong way around here, isn't it? Right, you look at the diagram. I'm not going to use my hands to say left or right. On my diagram, I've drawn a force acting to the right. That's given a negative answer, which means it wasn't a pulling force to the right, it's a pushing force to the left. And a pushing force is a thrust. Okay, right, let's see if I can finish within 20 minutes. Right, this section of the book introduced the names of some specific forces. You need to be familiar with them. There were also some important terms which they're going to use all the way through, which tell us how we can simplify our model. Something's a particle, it's no dimensions, we can ignore air resistance. The word particle implies no air resistance or drag. The word light, in reference to any part of the system, means you can ignore its mass. The word smooth, in reference to any part of the system, means you can ignore the friction, the contact force. Inextensible means a string, rope, cable won't stretch, so both ends will move together if it's taut, T-A-U-T. The examples are clearly showing you the link between Newton 1 and Newton 2 and the kinematics. Important to note at the moment the forces have been constant, so A is constant, so it's the Suvat formulae. Okay, can we also reiterate in Newton 2 it's resultant force. The F in Newton 2 is resultant force. We're going to have three forces beginning with R, resultant, reaction, resistance. The F in F equals ma is the resultant force. We're left with a chapter looking at gravity and weight. We separated the vertical motion when we did the kinematics, and there's going to be a mixed practice exercise. So my plan was second lesson this week is going to be the gravity and weight stuff, and one of the lessons next week will be mixed practice before we look at the last chapter we're going to do on the mechanics, which is the forces, more forces work. Any you like from 18C, but submit the even ones, okay? And then hopefully we're 1 week closer to seeing you back in school again. Cheers. Oh, and as always, email me any questions because we can relatively easily do worked solutions for them. Cheers.